Hello, let's walk through this problem. Let omega be the region bounded by the curves xy equals 4 and x plus y equals 5. Use Green's theorem to find the area of omega. So in these types of problems, it's really important to start by graphing the equations that you were given. So let's graph xy equals 4, which is y equals 4 over x. And then this can be written as y equals 5 minus x. So just by inspection, you should be able to tell that the intersection points are 1, 4 and 4, 1. So if you recall Green's theorem, it gives us a relationship between the line integral across the path C, which must be a simple closed curve, and the enclosed area D. So it tells us that the line integral along path C of P with respect to x plus Q with respect to y is equivalent to the double integral of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y along region D. And so this relationship comes in handy for this problem if you recall that a double integral with an integrand of 1 gives us the area of region D. We can set the integrand to 1 by setting Q to x over 2 and P to negative y over 2. That way, dq dx minus dp dy will equal 1. In order to continue with this problem, we need to parameterize curve C. So we start by looking at this segment, and then we can look at this segment of the curve. So for this first segment, we have x going from 1 to 4, and y is defined by 4 over x. So we can parameterize this as x equals t, where t goes from 1 to 4, and y equals 4 over t. Next, we parameterize the second segment of path C, which is along this straight line. And in that path, in the counterclockwise direction, x goes from 4 to 1, and y is defined by 5 minus x. So we parameterize that in the same fashion by setting x equal to t and y equal to 5 minus t. Now we are ready to set up the line integral. So we want to set up this line integral p dx plus q dy using these values for q and p. So the result is, and I'm going to simplify, the result will be half of x in the integral along path C of x dy minus y dx. All I did was substitute q and p in the expression for Green's theorem. And now that we parameterized both segments of the curve, we are ready to integrate. So first, let's write the integral for the first path. So this first integral will be half the integral from t equals 1 to t equals 4 of x dy, which in this case will be t times negative 4 over t squared. For dy, we just take the derivative of y with respect to t, and then we do minus y, which is 4 over t, times dx, which in this case is the derivative of x with respect to t, which is just 1. And we integrate all of that with respect to t. And in doing so, let's simplify a little bit so we get half integral from 1 to 4 of negative 4 over t times 2. So we can cancel out these. and we end up with negative 4 natural log of t from 1 to 4. And the result will be negative 4 log of 4. Next, we can integrate along the second segment of curve C using the second parametrization. So again, we use the same formula for the line integral that we derived using Green's theorem. But this time we go from t equals 4 to t equals 1. And in this case, x is still t, but dy will be negative 1 because it's the derivative of this expression. And then again, y will be 5 minus t, and dx will be just 1. And we simplify, so we get half integral from 4 to 1. We see that this is negative t minus 5 plus t, so the t's cancel out, and you end up with negative 5 dt. And when we integrate, we get negative 5 over 2 t, and we substitute 1 and 4, so that we get negative 5 over 2 plus 20 over 2, which gives us 15 over 2. And now the last step is to add the results of these two line integrals we did, because if you remember, when you do a line integral along several paths, as long as they are connected, you can add the two separate line integrals. So the line integral along C of this Green's theorem expression that we derived will equal the sum of the two parts. So 15 over 2 minus 4 natural log of 4. And this is also equal to the area of omega. So the benefit of using Green's theorem for this problem, instead of just setting up the double integral directly, is that it makes the integration a lot easier. Because first, we only need to integrate once rather than carrying out a double integral. And second, this simplification can usually lead to simpler expressions for integration, especially when it comes to trigonometry. But yeah, if you have any questions, let me know. Hopefully this explanation was easy to understand. And yeah, thank you.